Okay, class. Today we next we finish the topic the artificial starting solution related to the simplex method, and with this we will finish up this whole discussion on simplex method. So remember, we have done already lots of exercises on the simplex method. So one problem that can arise related to the simplex method is that if there is no starting solution. So just I give you an idea. So let's say this line over here, this is your area and your feasible region. I'm just giving an example. Okay, let me, no, wait, this one, no. So choose another pen. So let's say this is your feasible region. So it is some sort of lines that are intersecting, and this is your region, maybe like this. Okay, so this, so I have got these four corner points, and the in between, this is your feasible region. Now what's the problem for this feasible region is that normally, if you remember, we discussed before some slides somewhere before. Let me go back somewhere. That normally you start up with the 0 0 as your starting point of the feasible region. So for example, you start over here at the origin, and then you move around the corners, around, you can say, the boundary of the feasible region, in the direction where you rapidly see more improvement. So either it will be this B, or maybe it will be the other side where you see more change or more improvement. So now the problem that we have got over here, that if our feasible region, it does not include the origin, so it's highly likely, it's possible that maybe you have your constraints, they are aligned such that the origin, it is not included as a feasible point. So when it is not included as a feasible point, you can't start from this point. You are, if you try to start, you are beginning with a wrong step. So whole thing that will continue, that will come in the future, that will be wrong because your starting is wrong. So this is why we want to have an artificial starting solution. So for this purpose, when we don't have the original origin point as our starting point, in that case we try to create an artificial starting solution. So how it works, let's see. So if we have, why it happens like this, why it can happen this thing. Normally, if you remember from the previous cases, that all of your linear programming equations that you have discussed before, they had the constraints that had a less than or equal to sign. Okay, so again go back and you can check this thing easily, you can verify. So just over here, if I show you, so you have these constraints, and then you have the objective function below. So if you look at the constraints, all of these constraints over here, they have a less than or equal to sign, and except the non-negativity constraint, they are not real constraints, we don't consider like this. Okay, so your original constraints, they are all less than equal to constraints. Okay, so less than equal to constraint, and also their right hand side is positive, not negative. What does it mean, these two things? So if your linear programming constraints have less than equal to, and their right hand side is non-negative, it means normally that these constraints, they put an upper bound. Okay, for example, I say less than or equal to 5. Normally it means something below this line. Clear? So this is the case, and for example for this I have something like this, then it will be something under this line. So what happens is that less than equal to with non-negative right hand side, it normally offers us a nice starting point, nice starting basic feasible solution. Okay, but practically in the real life, in the real world, there are many constraints where you will see pure equal to sign. So equal to means it is not inequality, it is an equation or equality. Okay, and there are many constraints where you will have greater than equal to. Okay, so in such problems where you see such type of constraints, you don't have an easy feasible solution. For this purpose, then what we will do is we will introduce new artificial variables, and we call them these linear equations. We normally call them, they are ill-behaved linear programming equations or linear programming problems. Okay, they are not behaving normally. So for them, what we do is that we try to create the artificial variables that will help us, that will play the role of slack variables. So remember, if in the previous problem, these constraints you see over here, these three constraints, normally we take these constraints and we convert them into equations equal to sign, and what we add? Yes, we add slack variables. So for example, S1, S2, S3. Okay. These slack variables are very important because these slack variables, they give us a starting solution. So let me go back and show you somewhere you must have seen a starting solution. So I don't know where it was. So here you see, for example, if you remember the whole discussion, these four are the basic variables, and x1 and x2 are non-basic. So when x1 and x2 are non-basic, we say initially that they are non-basic, they are not important, we make them 0. Okay, so when you make them 0, then in each of these equations it's very easy that you make these two terms 0 and your starting solution is s1 equal to 24, and similarly you have s2 equal to 6 and s3 equal to 1 and so on, s4 equal to 2. So this gives you one basic starting solution for all the s values. Okay, now if you don't have a slack variable, then it's not possible, you can't do like this. Okay, so this is what happens. So you see over here, Tableau defines the current corner point by specifying the basic variables, and you set these values. This gives you the starting solution. This is your first. It's not feasible definitely, but it is at least part of the feasible region, this solution. Okay, then you try to improve it. But if you don't have starting solution, then you have to do something indirect, and that's what we do over here. We try to introduce the slack variables in terms of artificial variables. Okay, so for this purpose we will see these two methods, M method and the two-phase method, that will help solve this problem. Okay, so M method first. So it starts with the linear programming problem in the equation form. So same thing that you have been doing since long time. And what you try to do is that if the equation I does not have, so let's say if you have three equations, out of these three equations, equation number 1 is maybe correct, but equation 2 and 3 don't have slack variable. So in that case, what you do is that you attach an artificial variable r. So ri means it will have numbers. For example, first artificial variable is r1, r2, r3. We put over here capital R. Just for over convenience, this notion is used so that we keep them separate from the other variables. Okay. Why we want to keep them separate? Because remember, we are introducing them artificially. They are not real. we want to remove them at the end of the whole exercise. Okay, so we add these artificial variables to form one starting solution, but to remove them at the end, because I said that they are not real variables, so we don't want them to affect our objective function. So for that purpose, these artificial variables, we assign them a very high penalty, very high coefficient. We attach a very high coefficient to these variables in the objective function. Okay, so when you add a coefficient with these artificial variables, this will technically, when you start calculations, this will force them to zero eventually, not in the first step maybe, but eventually they will become zero in the optimum solution. Given that, the problem now will have a starting feasible solution. So let's see the example. And what type of, one more point. When you assign the penalty for the artificial variables in the objective function, so in the objective function, when you add a coefficient, normally you will put a very, very big number, as big as maybe just nearing the infinite. Okay, so you will put a number, for example, minus m if it is maximization problem, or plus m if it is minimization. So first I show you the example, it will be clear, then we can come back. So here it is, your equations. Now pause the video, think over it, and give me the idea what is the problem with this equation. So here you can see over here, this type of question can come to you in the exam. Okay, so always try to do it first yourself, then try to look at the answer in the slides. Okay, so this is your objective function. Clear, no problem. Here you have got the first equation. What's the problem? The first equation, it has got equality. Already it is equal to sign. So how to put a slack variable when it is already equal to sign? Okay, slack basically represents, if you remember, slack is added to convert the inequality into equality. So we can't do that. And over here you have greater than equal to sign. So here you will have to add the surplus variable, not the slack. Okay, and the third one, it's the normal equation, it's the correct one, it's less than equal to sign. So remember, this is important step, that in simplex method the constraints should have less than equal to sign. That's important thing. If they have the less than equal to sign, then they are more likely solvable. They will be easily, you can easily solve them as compared to others. Okay, so we continue. Next, we use the, so here we introduce some variables. They have given them x names instead of giving it like s or something. So I don't think it's important, it's up to you. Okay, here they have given x3 as a surplus in the second equation. So here, okay, so this one. And remember, because it's a surplus variable, you will subtract it, you will not add it. Okay, remember, the left hand side of this equation, it is greater than or equal to 6. So if it is equal to 6, no problem. Okay, but if it is greater than 6, then you would like to subtract that greater value, which is the surplus variable. That's how you make it equation. And for the x4, you have got a slack variable, so in the third constraint, so that's the normal. And for the first equation, you don't add or subtract anything, you don't need anything. Okay, so this is your now the equation form. Okay, next what we do is that equation 1 and equation 2, they lack the slack variables, so we need to add artificial variables, and we call them R1 and R2. Okay, And when we add them, so now you see there were already two variables. This is slack variable, no, this is surplus variable, this one is slack variable. Here we don't have any variable, and we add two more variables. One is R1 and the other one is R2. Okay, these are called our artificial variables. That's why I told earlier that we will give them a separate representation. They are given capital R series. Okay, so one more thing that we do is that we introduce these variables in the constraints, and then we have to put them, because remember the slack variables or surplus variables, we put them because we want to convert inequality into equation. Okay, but these variables, the artificial variables, they were not needed over here. We put them ourselves. They are artificial. So when we put them in the constraints, you have to put them in the objective function also. Clear? Very important point. You have to put it in the objective function also. And remember, because we are producing them ourselves, they don't exist naturally, we put over here the penalty for them. So penalty, for now it is shown as M, but in the practical cases we will put a number over here, maybe 1000, 2000, 10,000. M, capital M, means that it's some number that is very very big as compared to the rest of the equations. Okay, so we put a penalty in the objective function for this purpose, and remember we put over here plus M. So if you remember this exercise over here, it is the minimization problem. So if you go back, just what I discussed over here. So artificial variables, we will assign the penalty. The objective coefficient for this penalty will be plus M if it is minimization problem. But in the case of maximization, it will be minus M. So be careful, very very careful. If you make a mistake here for plus or minus, whole answer will be wrong. Clear? So this is it. We do this. When we are doing this thing, now we are almost ready to start our solution. Now when we have done this thing, now we have got these artificial variables that serve as our basic variables. So these three, you can say, R1, R2 and X4. X4 is already a slack variable. Okay, so these three, they give us the basic solution, and their value, the basic solution, starting basic solution is 3, 6 and 4. This is our starting basic solution. Is it clear? Pause it and think over it. I give you one more example, okay, and that will help you to understand. So let me go to the book. So if you remember the book I shared in the previous lecture, so go back to that book, and over there I have an example. So it is the topic, I did not discuss this topic yesterday in the last lecture, 9.5, the mixed constraints. So this is the problem of mixed constraints we study today. Okay, so we would try to find maximum for an objective function given or subject to mixed constraints. Mixed constraint means maybe one is greater than, one is smaller than, and so on. So here it is, the problem. There is an objective function given, and then there are the constraints, and you have got over here three constraints. Constraint number 1, it is the good constraint, the one that we like, but the constraint number 2 and 3, they are not good constraints because they will produce surplus variables. Okay, so it is a maximization problem. We want to maximize our objective value Z. So we have got from this, we convert them, these constraints, inequalities, into equality. We add over here S1 for the first constraint. This is our slack variable. But for the other two inequalities, we have the problem. We will add, we will subtract. Remember, surplus is subtracted. So we will subtract the surplus variable, which is S2 and S3. Clear? Now with this, we start the Tableau. So to solve the problem, we try to solve it. Now, why I'm doing like this? Basically, I want to show you if you don't introduce artificial variables, what problem will come. Okay, so this is what they are doing. They are directly trying to use the slack and surplus variables and trying to use them to solve the Tableau. Okay, so we take these values, we have created three equations. Now we create the Tableau, the initial Tableau. So here you can see the same things, same values are given. So remember, the Z value or the Z row is given at the end. All others are given over here because the coefficients for surplus variables are negative. So you put over here -1, -1. Clear? You can pause the video and just make sure you understand this Tableau. So what happens next is that from this Tableau we get our starting solution. So remember, in this case, when we are starting, we normally have these variables, the S series. These are our basic variables, whereas the original x1, x2, x3, they are non-basic. So we make them 0, for example, and we say that these three are our values. So S1, S2, S3 over here, it will be 50, 36 and 10, but with minus. Because there is a minus here and here, it will become -36 and -10. Okay, because if all other variables are 0, so your answer or your equation will be minus S2 equal to 36, which will be same as S2 equal to -36. Now the problem is this is not a feasible solution. This is not a valid solution because surplus variables, they represent some value. You say that, for example, your company has got 10 kilos of surplus cement. You cannot say that your company has -36 kilo of cement. These values can never be negative. If your solution is correct, these values can never be negative. I hope I make my point clear, and I wanted to show you what is the problem if we don't use artificial variables. What will happen? This is the disaster that will occur. Okay, so basically your surplus variables, slack variables, it's okay because they always give you positive value, but surplus variables, big problem because they will give you negative starting solution, which is not correct, which is not possible. So when you have a bad starting solution, you cannot go further. Okay, so what you try to do is that maybe you try to remove the surplus variables from the current solution, and for this purpose what they do over here, you see, they are using something as trial and error method. Now this is a big problem. Trial and error method means, or it is also called somewhere in the books called as hit and try method. Means we will keep on trying and there will be an error and we will try another until we see a success. So there is no guarantee. That's why this method, this approach is bad. That's why artificial variables are preferred in many cases. Okay, so what they are trying over here, for example, so same thing. If you remember, from the non-basic variables, you try to select one variable which can enter. Okay, so because it's maximization problem, you choose the highest negative value, so it is -2. So this one you select as entering variable x3, and in the departing variable you will select based on the ratio. So ratio, the least positive ratio will come out to be this one, 10, because this will be 10, this will be infinity, this will be 50. So you select as 3. So you select it, you keep on doing, and then you will get this solution. Here you get value for S1 is 40, S2 is -36, still negative. So again this is not correct. This is bad solution. So you keep on doing, it's a trial and error method, and until hopefully you get a good starting solution. Okay, so now come back with this idea. This is the problem if you don't use the artificial variables. That's why we put over here these artificial variables, so that we don't have to use those trial and error methods. Okay, so what they do over here is that they have got a valid starting solution, because the variables, artificial variables, they have positive values, 3, 6 and 4. Okay, so for, I told you before, for practical purposes we use value for m. When we are starting to solve the equation, we put m with some big value. So how big a value should be selected? Here they have selected 100, but practically you will select a value that is big enough that it can be differentiated from the rest of the table. So for example, rest of the table, the values are mostly in 1 until 10 or maximum 20. Then you can select a value of 100 over there. Okay, but it should be considerably bigger than the others, so that it looks as if it's like a very big penalty, like an infinity. Okay, we don't put an extremely big number, for example 1 million, because we will be using them in calculations. If I am putting over here 1 million, 1 million, it will make my calculations more harder to solve. Okay, so this is our starting simplex tableau. So here you see R1, R2, they are 1. So if you see, these are our basic variables, and basic variables, they have the same structure if you remember, 1 0 0 0 1 0 and 0 0 1. Clear? So what we do next is we make the basic variable coefficients 0. It is not completely in the correct format. So remember, if you go back and you check the basic variables, go back somewhere, you see the basic variables over here. The basic variables, so S1 is not basic now, but let me go to the first one. So here you see the four basic variables, S1, 2, 3, 4. The whole column is 0, including the Z row. Okay, so its pattern is 0 1 0 0 0 and like this. Okay, but in this case that we were seeing now, it was not fully 0. There are some values here. Okay, these are the artificial variable values. We have to make them 0 if we want to say that this is the complete, these are the complete basic variables. We have to make them 0. So how to make them 0? That's the same formula we have used so many times. Take the old value of Z. Okay, so and what you do is you add with them these two row values, 100 multiplied by row 1 and 100 multiplied by row 2. So first time in this Z value you add 100, you multiply 100 with this row and then add it to Z. Okay, and then you multiply 100 with this row and you add it to Z. Okay, so these two you will multiply, so rest it will be, for example, 300, 100, 100 and 300, and you will add it over there. So it will become almost, I think, because you are adding, so it will become 296 and 99, 0. Here it will become 0. Here it will be minus 100, 0 and 300. So let's see. So it will come out like this. You see over here. After two operations, because remember, there will be two operations of addition. This one and then this one. So try it. Take a paper. Do it yourself. Now I hope you have more confidence. I have given you a lot of examples in the last lecture. So here you have got a lot more. So you see x1 this, and you see that these are basic variables are now in the correct shape. Okay, when they are in correct shape, Now you can proceed to find the entering variable. In the previous case, you can't apply. No, because the basic variables are not in the proper form, you cannot apply the rule of finding the entering variable. But when they are in the correct form, now you can try to find the basic entering variable. So if you had tried on the previous slide finding the entering variable, because it's I think maximization or minimization, so you will try to find the most positive value. You don't have any positive value, so maybe you say I finish it up, or maybe you try to select this 0 x3. But here now you will see you have got three values and non-basic, and this one is the most positive. So for minimization you will select the most positive, and that will enter. And which one will leave, that depends on you take the ratio of this column with the solution column. Okay, so I don't know, they have done it, and it seems that it is ratio will be 1, and it will be 6 by 4 is 1.5 I think, and this will be 4. So definitely this is the minimum positive value, so R1 will enter, R1 will leave. Clear? Next you apply the Gauss-Jordan, and now they have given the simplified version. Now I think you already know, you have done so many practice, and we will not go in detail. You can do it yourself, and if there is still problem, then you can ask me. And but what they find out is, remember, the basic variables are written on this side. So the basic variables were R1, R2 and X4. Okay, so R1 leaves and X1 enters, and finally X1 is here, and R2 is there, and X4 is there. Okay, next when you proceed with the next one, so because X1 is your basic variable and R2 and X4 are basic variables, you try to check out your entering variable. You will see the most positive value is for the X2, so that will be your entering variable. And again, when you take the ratio of this column, you will find out that your R2 is the leaving variable. Okay, and based on that you will find out that when you will again do the complete iteration, you will find out the optimum value, which is this. Okay, so we have solved finally the problem by putting over here two variables, and these variables are, because you put high penalty in the objective function, they will automatically finish up. Okay, if they are not finishing up, then you will see something like this that's given over there. Where is it? They will be, when you put a very high penalty on the objective function, it will force them to become zero in the optimum solution, and they will become zero if there is a feasible solution. Okay, if there is for any reason they are left, then the problem has no feasible solution. Clear? So this was first part. In the WhatsApp group you can ask questions on this, whatever questions you have. Here is a problem given to you people. Do it, try to solve it. This is your assignment, and you people will take your time. I don't have hurry, because remember, this is maybe like your last of the assignments. After this I'm planning that after this chapter of simplex method, I will introduce two more chapters, and that will be our course. So we had more plans to introduce more things, but now you see the situation. So in that case, we don't have a capacity So I am planning to have at least 2 chapters. So those 2 chapters, I don't think they will have such numerical. They are more theoretical. So they will not have any numerical things. So this is your practice, plus it will be also your assignment. So assignment, do it, and you can submit it to me after when you come back, or if you want you can submit uh, if you people are coming to the university for any reason, you can submit, put it in my office, or if you want you can scan it and then you can, or leave the scanning part. When you come back after the holidays you can give it to me at that time. Okay. Next method is two-phase method. Now there is one problem in this method. If you see that you have to decide a very big variable, a very big number, the coefficient for the artificial variables, and you are not sure how much big value it should be. If it is not so big, it can mix up with the other problem values and it can give you problems, not correct solution. Okay. And if it is too big value, then it will take too much computational time. So there is another method which does not have these issues, that is called two-phase method. Now in this method you have two steps or two phases. Okay, in the phase 1 we attempt to find out the basic starting basic feasible solution, and we put the problem in the equation form and we add the necessary artificial variables to the constraints, and then we find the basic solution of the resulting equation that will minimize the sum of the artificial variables. Okay, so let me show you example and then we come back to this. So I will discuss this diagram also. So here it is, the same problem you have done now. So you have got two artificial variables, you remember, R1, R2. Okay, initially, now this is not your objective function, this is not your normal objective function. Okay, initially for the first phase we create another objective function where we say that we want to minimize the sum of these two artificial variables. Okay, whatever they are, we want to minimize it. So this is our first phase of the problem where we want to minimize these two values. Okay, that's our objective. So we put it over here in the equation form. So if you make it into equal to form, so R minus capital R1 minus capital R2 equal to 0, it will give you these two coefficients. Okay, minus R1 minus R2, and the others it is the same story you have already seen. Okay, so remember that this is the basic solution given based on the artificial variables, and initially you have got these basic variables R1, R2, X4, and you need to manipulate them. You need to proceed as we have seen in the simplex method, and you do the same steps for entering and leaving variables, and finally you will reach for this one. So here, and you will reach for these basic variables. So these one x1, x2 and x4, they become the basic, and the artificial variables, they become non-basic. Okay, so they leave, and x1, x2 and x4, x1, x2 enter, and x4 was already there. There was some mistake over here in the slides. Please check your notes and correct it. There was a mistake over here. And there were some values given, whereas these are the basic variables, so their column is in this pattern 0, 1, 0, 0. So I leave this calculation onto you people. You already now know how to manipulate the simplex tableau, and I suggest that you go through it and take this initial form, this one, and then do all those calculations for entering and leaving variables, and make sure that you can get these you can reach this step where you have these three basic variables. So Now you will stop in the phase 1 when you have this step where you don't have the artificial variables as basic. So when artificial variables they become non-basic, okay, so this is very important point. You will stop over here when the artificial variables are non-basic, and then the other criterias are met. For example, so remember this was a minimization problem. So remember this is minimize. So if you remember in the case of minimize, you check the non-basic variables and you check if they have any positive value. So in the non-basic variables over here, you don't have any positive value. There is only 0, but there is no positive value. Okay. So you will stop, and this will give you one optimum starting point. So we have not done the complete solution. This is only the starting point. This only gives you the starting point. This is the phase 1 of the two-phase method. Okay. So you will stop, and then you will get over here the values for your basic variables. So basic variables are x1, x2 and x4. So these x1 here, because non-basic you make them 0, so all these three you make them 0. So automatically when you consider them 0, so x1 gives you the value of 3 by 5, x2 gives you 6 by 5, and then x4 gives you 1. Okay, so you stop over here. This gives you the new equations that you will use for your constraints. So your original equations, if you see, these were your original equations, you will modify them. Okay, that was the purpose. That's why we used this specialized objective function, where we wanted to minimize the small r, which is the sum of the two artificial variables. Clear? But of this step you will remove your artificial variables and you will move to the phase 2. But the most important step that I want to emphasize again, you can only stop when all the artificial variables, because you will remove artificial variables, you can only stop when all the artificial variables are non-basic. If any one of the artificial variable is in the basic list, you cannot stop. Then you will try to see if you can swap the artificial variable. You select basic variables, then you will forcefully consider it as the entering variable. Is it clear? So think over it. Try to go through the examples. The unfortunate thing is that Cengage book, they don't have example about these two methods. I will try to search some other material where I can see some good examples for these two methods. So if we get some more hands-on practice, then it will be great. Okay, so this is the summary. We were doing two-phase method. So in the two-phase method, in the first phase, we are now in the first phase, we introduced the artificial variables just like in the M method. And what we want to do is that we want to find out the basic feasible solution. So I gave this example many times to you people that simplex method, it means just like for example this irregular shape, you can say this is maybe a stone. This shape represents your overall possibilities of feasibility possibilities. This represents your feasible region that is defined by all the set of constraints. So if you have a lot of constraints and you have more than two variables, then your feasible region, it will be something like this. Okay, so feasible region is like some solid shape. And what you want to do by phase 1 and phase 2, so the phase 1 wants to find out some point on this surface, not inside this, not outside, away from this area. So if this is your feasible region, I cannot start outside. For example, over here, I cannot start this, I cannot select this point as a feasible, basic feasible solution. That's the problem. I have to start somewhere on this surface. That was the purpose of phase 1, to find out the basic feasible solution. Once we have found one the feasible point that is part of the solution, that is valid point, then we will go to phase 2, which is just like the simple M method, that we will be going around, which you can say that this is just like your normal simplex method. You will go around on the surface. So remember, simplex method only goes on the top of the surface. So it goes on the top of the surface trying to find out the best method and the optimal solution. Clear? So this was it. And in phase 1, we over here went through all these steps, and finally we reach a point where all the artificial variables, they are non-basic, so we remove them, and also the other conditions are met. So none of the non-basic variables, they are positive. So we stop over there, and then we say that this is our basic feasible solution. So these values, we take these values, what we do next? We move to phase 2. So in the phase 2, we delete the artificial variables, artificial columns, and rewrite our original problem. So this is now your original objective function. And then we change, now we have the different constraints. These are not the same constraints you saw before. So if you go back, so you see constraints over there, you had the basic. So if you want to even go more further back, so it was something like this: x1, x2, and then it was x3. No, is it same? No, it's not same, I think. So this one over here, it was 3x1 plus x2. We added this r1. Okay. Similarly, there was over here something. So this was the surplus variable over here, and we added this surplus, and then we added artificial r2. Okay. So we had 3 equations. Now you check these equations. Now they are totally changed. Now we have got x1 and x3, and then we have x2 and x3, and x3 and x4. So over there it was what? x1, x2, and again it was x1, x2, and x1 and x2, and x4 and 3 were added. So basically we had 3 equations in x1 and 2 only, and we added the surplus and slack variables, and then we added the artificial variables. Here we have totally changed it. Now we have got 3 equations, and these equations are now represented in terms of the original variables plus the slack and surplus variables. Clear? So this is the result of the first phase. The first phase, it transforms the original constraint equations to give a starting feasible solution which is valid, correct, if it exists. If it does not exist, you will stop over here. You will not get the optimum values over here. You will have the artificial variables that will have the values still over there in the columns. So this was the phase 2. This was the phase 1. In the phase 2, we proceed normally. So you take these columns over here. So this is your Z row, then the first constraint, second and third. So we take them and we make this simplex tableau. Now this is your phase 2 is now your simple calculations for the simplex that we have done so many times. So -4, -1, and so on. So remember, this is still minimize. Okay. So in minimize, what we want to do is, so here we have removed our artificial variables. Now we have only x1, x2, x3, and x4. Okay. So we eliminate the non-zero coefficients of x1 and x2 in the Z row. So remember over here, because these are our basic variables. Okay. So we have got these 3 basic variables, x1, x2, and x4 from our previous problem. Do you remember this basic variables? Now these basic variables, they are not in the proper format. So if you go back here, you see the proper format is 0, 1, 0, 0, or 0, 0, 1, 0, or 0, 0, 0, 1. So they are not in their basic format, so we have to correct them. So to correct them, we have to remove this, and this one is correct. Okay, so we need to eliminate non-zero coefficients of x1 and x2 in the z row. Okay, so you already know how to remove it. What should we do? So this is it. What we do is that we take this value. So this is the one. We will use this row as a tool to change this row. So how to do it? So this is 1. So I will multiply this row with 4. So it will become 4, 0, 4 by 5, 0, 12 by 5. And then when I get the 4, I will just add it to this row. So it will become 0. So I will add it to this row and the result I will save on this row. Okay. Like this I proceed, and this is the result over here. Now this is the result I get. I got 0, 0 and 0. So these three are now my basic variables. So I want to minimize. So remember, basic variables, they are always 0. So I've got them 0. In the minimization problem for simplex, remember it is minimization. So what I do is that I will check the non-basic variables. Over here I have only one non-basic variable. So I check that non-basic variable if it is positive. If it is positive, that will be entering variable. If it is not positive, I will stop. I have reached the optimum point. So you remember these exercise. Okay. Practice, that will make you perfect. Only with practice you will remember these steps. Okay. So what I do over here is I select this x3 and it will be the entering variable. And then I will take this column and I will take the solution column, take the ratio, and that will give me the leaving variable out of these three. So these three, one of them will leave, x3 will enter. So I will keep on doing this thing until, so these are the same simplex steps. I will not go in detail. I will keep on doing until I'm done, I've finished. So I hope this was a nice introduction on the complete set of simplex issues. So this was one of the very important part of optimization methods, that is the simplex, that is taught in many disciplines, from business to computer science to engineering to many fields. This is the common topic that's taught, and simplex is one of the main topics in optimization courses. So with this lecture we finish up with the simplex, and now what my planning is that in the future, at least I want to have 2 more chapters for this masters. Now we are in a very strange situation, but at least 2 more chapters. So one of them will be quite easier one, which will be on heuristics. That is the topic. I will take it from my artificial intelligence course. So I teach it to the bachelor student also. So I hope it will be more easier for you people. So if they are studying, you people can more easily comprehend that. And the second one will be the last chapter. That will be a little tougher. That will be the last I discussed already. That is based on the differential mathematics and calculus. So this is it, and sensitivity analysis we have already done, I think. And is there anything left? So I think we did all this thing, all of these. Range of optimality, and then we saw this changes to the right hand side of the constraints. So now it all depends on you people for make sure to do a lot of practice. I have given this link also. This was one of the playlist on simplex methods, but I don't remember how it was. So maybe you can stick to that book from Cengage for the simplex method. I will try to search something that I can find new about these M method and two-phase method. So with this I will conclude this lecture. See you next time with some new topic.